Now we shall start the module 5 in BTD, basic thermodynamics, subject code 18ME33. This deals with real gases as well as ideal gases. Initially we shall look into the ideal gases part, and then we will go to the real gases part. Okay. As far as syllabus is concerned, very simple. It has nothing very complicated here. Very simple and straightforward things are there. So I thought I will handle it now. Like first part is ideal gases. We will study the ideal gas mixtures, Daltons Law of partial pressure, Amagats Law of additive volumes, evaluation of properties of perfect and ideal gas, air-water mixtures and related properties. So for each of these topics we will have one small video. Then we will come to real gases. We will deal with the introduction, means what are real gases and how they differ from ideal gases. We will go to the van der Waals equation of state. Then we will see the van der Waals constant in terms of critical properties. A small derivation is there. We will look into Betty-Bridgman equation. We will also look at the law of corresponding states. Then there is something called compressibility factor Z, that we will find out from the compressibility chart. And lastly we will see the difference between the ideal and real gases. An ideal gas is a simple compressible substance, a very unique kind of pure substance. So basically gases are compressible. Okay. And this ideal gas means it is like a pure substance. A perfect gas or an ideal gas is defined as a gas having no forces of molecular attraction. See, gas, when you talk of gas, suppose I am breathing out, so I am really releasing a mixture of gases. It contains like nitrogen, means air which controls nitrogen, carbon dioxide, oxygen. Okay, but it contains, this all gases contain lot of molecules. A perfect gas or ideal gas we consider which does not have any forces of molecular attraction. So these all molecules are independent and they do not attract each other. So a gas which follows the gas laws at all ranges of pressure and temperature can be considered as an ideal gas. So ideal gas is the gas which follows the gas laws for all ranges of pressure and temperature. So basically we have these two laws, that is Boyle's law and Chaude's law, what you have studied in 12th standard. Just to refresh, Boyle's law states that the volume of the gas varies inversely with the absolute pressure when the temperature remains constant during the change of state. Mathematically, when T is constant, temperature, there are only three terms. Please understand, there are only three terms: volume, pressure and temperature. Okay, and you can consider a piston cylinder arrangement. Simple. So what happens when the piston, if is compressing the air, then what happens? The volume reduces. Okay, pressure increases. Simple it is. So volume is inversely proportional to 1 by P. Volume is directly proportional to 1 by P, or we can say it is inversely proportional to pressure when T is constant. or you can write it in other way, PV is equal to constant. So for different states, we can write as P1 V1 is equal to P2 V2 is equal to P3 V3 and so on till Pn Vn. This is the Boyle's law. Means when temperature is constant, volume varies inversely to the absolute pressure. Now Charles' law. Here in Charles' law, the pressure is kept constant. Okay. So when the pressure is kept constant, what happens? The specific volume of the gas varies linearly with the temperature. So when you suppose you heat the gas, so when you heat the gas, temperature rises. When the temperature rises, volume also increases. This is the idea when the pressure is kept constant. The volume of the gas varies directly to the temperature when P is kept constant. So V is directly proportional to T, or V by T is constant. Based on these two laws, we will come to the ideal gas law. The ideal gas law, or the characteristic equation for gases, relates the dependence of pressure, volume and temperature and mass of a state. This equation can be derived from Boyle's and Charles' law. So we can say P1 V1 by T1 is equal to P2 V2 by T2, or continuing we can say Pn Vn raised to divided by Tn, and that is constant. Okay, the constant in the equation is called as gas constant and is represented by the letter R. Its value changes for different gases and be calculated if the molecular weight of individual gas is known. So here for different gases, this R, this is a gas constant. Gas constant means for a particular gas. There is one more constant that is known as universal gas constant. We will write it as R bar. Okay, that is different. That is standard for all the gases. But here what we are discussing, this is only gas constant, and it is different for different gases, and it can be calculated if the molecular weight of the gas is known. Now let us see this universal gas constant. So here to find out this, the term mole comes into picture. As the value of constant R is different for different gases, another unit of mass called mole, kg mole is used. The mole is the amount of substance which contains as many molecules as there are carbon atoms in 12 grams of carbon 12. Simple, you can just go through here. 1 kg mole of oxygen. Oxygen is nothing but O is 16, O2 is 32. So 1 kg mole of oxygen O2 is 32 kgs. Similarly, nitrogen N is 14. So N2 is 28. Okay. The 1 kg mole of nitrogen has a mass of 28 kgs. Simple term it is. See, carbon is 12 only. C is 12. So the molar mass of a substance containing n molecules is given by m divided by n grams per mole. There are two terms. One is grams per mole or kg per mole. The molar volume is the volume per mole of a substance. So the volume occupied by a mole of a substance is known as the molar volume. There in Amagats law, they had heard of Amagats law. He told very simple thing. He has told. Amagats proved that equal volume of an ideal gas at the same temperature and pressure has equal number of molecules. You take any gas, okay, if it is an ideal gas, if the temperature and pressure are kept constant, they will have the same number of molecules. He further put that at normal temperature and pressure, that is normal temperature pressure is 0 degree centigrade and 1 atmospheric pressure, the volume of 1 kg mole of a gas is equal to 22.416 meter cube. he found out that at NTP, that is 0 degree centigrade and 1 atmospheric pressure, 1 kg mole of a gas has a volume of 22.416 meter cube. 1 gram mole, so you convert it into 1 gram mole of a substance has 6.023 into 10 raised to 23 molecules, which is also called as a Avogadro's number. Okay. Now we can see here, if V is the volume of the gas with a mass m, then we may write the equation as PV is equal to mRT. Capital V is the volume. Okay, capital V is the volume. Small m is the mass here. Capital T means it is the absolute temperature in Kelvin, and R is the gas constant for that particular gas. Okay, now we can see if capital M is the molar mass, then the molecular volume is represented as this molecular volume we are writing as V bar. V on the top of it, we are drawing a line, we call it V bar, is equal to capital M into V. Okay, that is, we can write V volume is equal to M into V, mass into specific volume. Substituting in the equation, we get P V bar is equal to mRT. Okay, or P V bar is equal to R bar into T, where R bar is nothing but mR. This R bar is called as the universal gas constant, and the value of this R bar is nothing but R bar is equal to now P V bar by T is at NTP. V bar is equal to, we are as per Avogadro, 22.416 meter cube per kg mole. So substituting these values, we find out P is 10 raised to 5 Pascal, okay, into 1.01. This is the atmospheric pressure at NTP, 1 atmospheric. So 10 raised to 5 into 1.01, this is the P. Volume is 22.416. We multiply both of this and divided by T. T is temperature, that is 0 degree centigrade or 273. Because T is capital T, we have to take in Kelvin. It is 273. So when you substitute, you will get the value as 8314 joule per kg mole Kelvin. Or you can convert into 8.3143 kilojoules per kg mole Kelvin. So considering n moles of a gas, now you just understand this, that R bar, that is universal gas constant, is nothing but 8.3143 kilojoules per kg mole Kelvin. And when if you come to moles now, N into V bar is equal to V. Hence the equation becomes PV is equal to, earlier we are writing it mRT, now we are writing in terms of moles, N. So N into R bar into T. Okay. So N into R bar is equal to M into R, or N into M into R is equal to MR, or you can say N is equal to small m divided by capital M, where small m is the mass and capital M is the molecular weight. Now we shall look at ideal gas mixtures. The thermodynamic behavior of a mixture of gases depend on the individual properties of its constituent gases. Like air is also a mixture of gases. It contains around 79% nitrogen, 20% oxygen, then argon, carbon dioxide, etc. So the property of the mixture of gases depends on the individual property of the constituent gases. As substances in gaseous phase are readily miscible, okay, with each other, we can have a large number of gaseous mixture combination. So this miscible means they mix with each other. Okay. So because the gases can easily mix with each other, we can have lot of gaseous mixture combinations. Like you take air only. Now there are pollutants coming like different oxides of nitrogen, oxides of sulfur. These are all going now into the air. So they are all miscible. If homogeneous mixture of a gas has its constituents which do not react chemically and we have fixed proportions by weight, it can be considered as a single substance. So, if a homogeneous mixture of gas has its constituents which do not react chemically and have fixed proportions by weight, it can be considered as a single substance, like we consider air again. Here, the constituent gases, they do not react like nitrogen, oxygen, carbon dioxide, they don't react with each other and their proportion is fixed. That is why we call it as a single substance, air. Thus, a non-reactive mixture of gas is a multi-component system having constituents which do not react chemically with one another. Okay, please understand, you can just think of air only. Here it is a non-reactive mixture of gases in a multi-component system having constituents which do not react chemically with each other. This is the ideal gas. Now we shall look into mass fraction, mole fraction and molecular weight of a substance, and then we will go to the Amagats law and Daltons law. So the total mass of a mixture of is the sum of the masses of each component. Like again you can take air. Air has got like nitrogen, oxygen, argon, carbon dioxide. Let us take 4. So M is equal to M1 plus M2 plus M3 plus continue. Is equal to summation of I for all Mi. So if you divide this by M, you will get 1 is equal to the equation, top equation, M by 1, M is equal to 1 is equal to M1 by 1 M plus M2 by M plus M3 by M, so on. That is summation of I, Mi for every Mi divided by M. That is summation of I, Xi. The ratio Mi by M is defined as the mass fraction of the ith component, okay, in the mixture. That is a mass fraction. Now what is the mass? Suppose you, in simple terms, you take some laddu, besan laddu. So you have got 80% besan, 20% sugar. Okay. So you have put 80 kgs besan, 20 kgs sugar. It becomes 100 kgs of laddu. Fine. So now the mass fraction of besan is equal to 80 by 100, that is 80%. And the mass fraction of sugar is 20 by 100, that is 20%. Simple. This is how you calculate the mass fraction. I just told you about 2 components because here it can be more number of components also. As an easy illustration. And we are talking about gases, but I gave an example of solids. Not an issue. But that is also a mixture only. When an analysis of a gas mixture is made on the basis of mass or weight, it is called as gravimetric analysis. So there are 2 types of analysis. One is gravimetric analysis. The other is volumetric analysis. Okay. If you consider by mass, I think you have studied in chemistry, first year engineering chemistry. When you are dealing with mass or weight, it is called as gravimetric analysis. And when you do analysis based on volumes, it is called as volumetric analysis. Now let us take about, this was about mass fraction. Now we will come to the mole fraction. The total number of moles in a given mixture is given by N is equal to N1 plus N2 plus N3 and so on. It's equal to summation of II for all Ni. Dividing throughout this equation by N, you will get 1 is equal to N1 divided by N plus N2 divided by N, N3 divided by N and so on. That is summation of I for all Ni divided by N. You can write this as Ni divided by N is equal to Yi, where Yi is called as the mole fraction of the ith component of the mixture. Thus, by definition, Yi is equal to Ni divided by N. When analysis of gas mixture is made on the basis of moles, it is called as molal analysis. Okay, so now we have seen mass fraction, we have seen the mass fraction, and now the mole fraction, which is on molar basis. Having seen this, now let us see the two laws, that is Gibbs Dalton's law of partial pressure. Very simple it is. I'll use just see the three sketches here first. On the top, okay, you have got three gases, like three squares are given, three different constituents of a gas mixture. So you have mixture, and there are three components. So first is Vt, P1, N1, and second square you have got Vt, means volume is constant, temperature is constant, then pressure is varying, here is P2 and N2. Okay, and third is again V and T, that is volume is same, temperature also same, and the pressure is changing P3 and N3. So for a mixture, when you mix all these three, see, please understand, they don't react with each other. Okay, chemically they don't react. Like in the evening we eat snacks, mixture. So it will have ghati, it will have some what you call pulses. So many different things are. They don't react. They are separate only. Here also they are separate only. So when you take the mixture, now the big rectangle in the bottom you can see. Vt means the volume is same, temperature also same. But what has changed now? The N becomes N1 plus N2 plus N3. There are three constituents, and also the P becomes P, that P is equal to P1 plus P2 plus P3. So this is the Dalton's law. It says that the total pressure of a mixture of ideal gases is equal to the sum of partial pressures when the partial pressures are determined at the volume and temperature of the mixture. So very simple. I'll again repeat this statement. The total pressure of a mixture of a ideal gas is equal to the sum of the partial pressures, okay, and when the partial pressures are determined at the volume and temperature of the mixture. So here, as you have seen in this sketch, V and T, volume is fixed as well as the temperature is fixed. That doesn't change for the constituent gases as well as the mixture. It is not constant, it is actually constituent. That mistake, spelling mistake is there. It is not constant gas, it is constituent gas, means this mixture has got three constituents. So this is the simple terms, the Dalton's law of partial pressure. Okay. If you want to in mathematical terms, you can go through this, but the gist remains that the total pressure of the ideal gas is equal to the sum of the partial pressures of the constituent gases. Now we shall look at the Amagats law of partial volume. That was about pressure. Now this is about volume. Amagats law of partial volume is very simple here also. So you can see there are three constituent gases. Sorry, again it is not constant gas, it is constituent gas. Three are there. One box, second square, and the third square on the top, and bottom is a mixture one. Okay, so you can see P comma T, second one also P comma T, third also P comma T, and finally mixture also P comma T. Means the pressure is constant and the temperature is also constant, is same for all the constituent as well as the mixture. Okay. Now volume is changing. So earlier first constant gas has got volume N1, V1 and moles N1. Second one volume V2, moles N2. Third one, volume V3 and moles N3. So the mixture, when we have the mixture at the same pressure and same temperature as that of the constituent gases, then the number of moles N is equal to N1 plus N2 plus N3, and we can write the volume is equal to V1 plus V2 plus V3, because we are not changing the pressure or we are not changing the temperature also. So I'll read it. An ideal gas mixture can be separated into its constituent in such a way that each occupies a volume at the same temperature and at the same temperature and pressure as the mixture. So if you read out, the total volume of a mixture of ideal gases is the sum of the partial volumes of the constituent gases. We are written a V is equal to V1 plus V2 plus V3, means the V is the volume of the mixture is equal to the constant like V1 plus V2 plus V3. So I repeat, the total volume of a mixture of ideal gases is equal to the sum of the partial volumes of the constituent gases when the partial volumes are determined at the pressure and temperature of the mixture. Okay. So here the P and T, pressure and temperature, are kept constant. Then V, the volume of the mixture, is equal to sum of the partial volumes of the constituent gases. This is known as the Amagats law of partial volume.